Okay, welcome everyone to the 2022 Medal Talks. Bienvenue à tout le monde pour les conférences pour les médailles de l'ACP 2022. Unfortunately, this year, the 2022 Medal Talks had to be done by Zoom. We did not get the call out early enough, and so we can't have double Medal Talks at the 2023 Congress. So today we have, first of all, David London, who is at the University of Montreal, and he won the prize in theoretical and mathematical physics given by the CAP and the CRM, which is the Centre de Recherche Mathématique. And second up will be Asmina Arvinataki from the Perimeter Institute, who won the Vogt Medal in subatomic physics. And third up will be Charles Gale from McGill University, who got the CAP Medal for a lifetime achievement in physics. We will go with a 25-minute talk, followed by a 5-minute question and answer period. Then I will read the citation, and then we will ask the medalist to give a short acceptance speech. So let us start with, thank you for joining us today. And David, please take over.
Okay, so I do theoretical particle physics. And in particle physics, the ultimate goal is to find the so-called theory of everything. That is, we want to be able to describe all the particles of the universe and the forces with which they interact in one mathematical framework. And the idea then is to describe physics at all energies. And that will allow us to understand the evolution of the universe. A first step in this direction has been made with the development of the Standard Model. Now, the Standard Model is based on a gauge group, SU3 cross SU2 cross U1. And here, the SU3 color, the first one, represents the strong force. It basically is QCD. And the second part, SU2 cross U1, is the group that unifies the electromagnetic and the weak forces. So the idea is that this is the symmetry group that exists at high energies, and it's broken at the weak scale, which is about 250 GeV, to what we see at low energies, what we see in our world. SU3 color, the strong force, and U1 electromagnetism, that is to say the electromagnetic force. And this breaking is accomplished by the Higgs boson, which also gives mass to all the particles. And the Higgs boson was discovered in 2012. So this is the gauge structure, and there are gauge bosons associated with it. And in addition to these particles, the Standard Model also contains 3 generations of quarks and leptons. Now, the Standard Model has made many predictions. Virtually all of them, or almost all of them, have been verified. It's clearly correct, and in fact, the fact that we have such a model, such a theory, that's one of the great achievements in modern physics. This said, we believe that it's not complete. There are any number of reasons. I split them into philosophical reasons, philosophical in quotes. By this, I mean things that are not really physics reasons. There's a large number of arbitrary parameters. There are many unanswered questions. We haven't unified all the forces. Now, these are not physics reasons in the sense that there's no particular reason that the theory of everything has got to satisfy all of these, but there are other reasons, and specifically there are observations that the Standard Model can't explain, namely neutrino masses. The Standard Model predicts that the neutrinos should be massless, and they're not. There's no candidate for dark matter. It can't explain the baryonic symmetry of the universe, and there are other things of this type. The point is that there's got to be physics beyond the Standard Model. And my research has focused my entire career on the search for this new physics. So I do what's called phenomenology. And so I'm a theorist, but there are close ties between theory and experiment in what I do. So when I talk about the search for new physics, I'm talking about theoretical searches for new physics. And from this point of view, there are a variety of ways to go about doing this. One way is to just build a model of new physics that contains new particles. And the idea is to look for the experimental signatures of such a model. And here there are two ways of doing so. One is to basically look for the new particles that are predicted by this model. In other words, to search direct searches experimentally. And the other way is by indirect signals. That is to say that the new particles will contribute to some observables, but virtually. And so the signal will be then a difference between the prediction of the standard model and the value, the measured value of the observable. A second thing to do is to look at experimental results and see how they constrain various new physics models. And above, I talked about these indirect signals where you compare the measured value of an observable with its standard model prediction. Well, that assumes that we know what the standard model prediction is. So another thing that I've done is to actually calculate the standard model predictions for various observables. And then finally, if there's a measurement that disagrees with the standard model, the idea is to come up with some new physics explanation for this disagreement. You can do things model independently, just determine the properties required of any new physics model in order to explain the data, or you can construct explicit models. And in my research, I've done all of these things. Okay, and so in this talk, I'm just going to give you a number of examples of the things that I've done in the search for new physics. In the 1980s, superstrings became very popular. The most popular kind of superstring theory at the time was called a heterotic string, which had some large gauge group at the Planck scale. And at low energies, which means basically 10 to the 15 GeV, it was broken to this grand unified theory E6. Other guts that had been previously studied were SU5 and SO10, and they're in the E6. So E6 gets broken to SO10 cross U1. When you see a U1, it means that there's an extra Z prime boson. And then the SO10 is broken to SU5 cross U1 with a different Z prime boson. So the point is that the E6 gut contains two new Z prime bosons, what we call the Z psi and the Z chi. And this was towards the end of my graduate studies. With my advisor, we looked at extra Z primes coming from E6. And we said that the most general Z prime would be a linear combination of these two, which we call the Z of theta. Anyway, and so we just parameterized it in this way and looked at branching ratios, constraints on this Z prime. Basically, we looked at ways to detect it. And in fact, when experiments looked for Z prime bosons, they pretty much used our formalism. This said, of course, they didn't find anything. The subject for which I'm probably best known is CP violation in the B system. CP violation has been seen in the kaon system, and it's explained in the standard model by the addition of a phase, an imaginary parameter, I eta. Eta is real, in the CKM quark mixing matrix. One convenient parameterization of this phase information is the so-called unitarity triangle, in which the sides here involve magnitudes of CKM matrix elements, and then the interior angles are CP violating angles, all proportional to this phase eta. And so the idea then is to test this explanation, and that's tested by measuring alpha, beta, and gamma independently to see whether they add up to 180 degrees and to see whether they're consistent with independent measurements of the sides. And the B factories, Babar and Bell, were built in order to do this, and they were basically built in the 90s. Now, in the late 80s, there were plans about how do we measure alpha, beta, and gamma. And the idea was to measure CP violation in these decays. B going to psi k short for beta, pi plus pi minus for alpha, and BS going to rho k short for gamma. And this was based on the assumption that these are tree-level decays. But the thing is that they're not. And so Roberto Pache and I pointed out that these decays also receive what are called penguin contributions, which will ruin the clean measurement of alpha, beta, and gamma in these decays, or which could ruin. And so one has to deal with this so-called penguin pollution. And so in 1990, Michael Gronow and I showed how you can remove the penguin pollution from B0 going to pi plus pi minus and cleanly extract alpha. Basically, what you need to do is to combine information from B going to pi plus pi minus with information from other decays that are related by isospin. B plus going to pi plus pi 0 and B0 going to pi 0 pi 0. And when you combine all this information, there's enough information to remove the penguin pollution and get at alpha. And this method is basically the standard method to measure alpha and was used by Babar and Bell to make their measurements. Because of the penguin contributions, this decay, which was planned to measure gamma, BS going to rho k short, doesn't work anymore. It just doesn't work. So Michael Gronow and I pointed out an alternative where there are no penguin contributions. Basically, we looked at the 3 decays, which once again are related to one another. B going to D K short, D bar K short, and something called the DCP K short. And once again, the idea is to measure all 3 decays to extract information. And from all this information, gamma can be extracted. A little bit later, what happened was that Michael gave a talk in Switzerland, and Daniel Wieler was in the audience. And so he said, hey, wait a second, these all use neutral BDKs, but the same thing can be done with charged BDKs. And so they proposed a slight modification, the same idea, but just using charged BDKs. And those are easier experimentally. And so the so-called GLW method is now one of the standard ways to measure gamma, and it's been used by all the experiments. Another subject that I've looked at is effective Lagrangians. In the early 1990s, there was a much interest in a certain type of new physics model. The new physics model had to not have any new gauge bosons, that is to say the gauge group was SU2 cross U1, and that the new physics couples mainly to electroweak gauge bosons, and it's heavy. And so this type of new physics was studied, and Peskin and Takeuchi showed that you could parameterize all the effects of new physics with the addition of 3 new parameters. S, T, and U is what they called them. And these are known as oblique corrections. So we took a look at this, and we said, what happens if the third condition at the scale of new physics M is much bigger than MW and MZ? And so we decided, what happens if this is relaxed? So this could happen if, because of this condition, we neglect these terms that look like mz squared over m squared. So what happens if we don't neglect these terms? This can happen either because m is small, the new physics is light, or because the measurements of the observables are very precise, and so you need to consider these new corrections. We showed that all of this could be understood with the addition of 3 new parameters, which we called with not much imagination, V, W, and X. And anyway, so we showed that these additional corrections could be parameterized by these 3 new parameters. Okay, I'm going to jump. So this paper, the paper with VW and X, didn't make a big splash when it was first published in the 90s. Let me jump forward 20 years later. That's to say today. Today, no new physics has been found, so now the new physics is believed to be heavy. So there is no light new physics, and the standard model is viewed as the leading term in an EFT, in an effective field theory, and that's often called the SNEFT. Nowadays, the SMEFT is very popular. A lot of work has gone into tabulating all the operators of SMEFT, and one also basically one writes the observables in terms of all these new physics parameters, so that if you measure something and find a disagreement, you'll know which new physics operators could be involved. And the point is that now the observables probing the oblique parameters are very precisely measured, and so you have to take into account these higher order terms, V, W, and X. So even though, as I say, the paper was not particularly noticed when it was published, now, 20 years later, it's quite relevant. So who would have guessed, I say. In 2013, LHCb measured an observable called P5 prime, an observable in the angular distribution of B going to K star mu mu, and found that it differed from the standard model prediction by a good amount, almost 4 sigma. And there were other observables that were measured. Together, they suggested that there's new physics in B going to S mu mu. There was also another set of measurements. In 2012, Babar measured RD and RD star, which compares the branching ratio of B going to D tau nu and B going to D mu nu or E nu, and found that this ratio disagreed with the standard model by 3.5 sigma. These measurements were repeated by other experiments, namely Babar later, and then Bell and LHCb, and these results were largely confirmed. And these suggest that there's new physics in B going to C tau nu. These two sets of measurements, new physics in B to S mu mu and new physics in B to C tau nu, are known as the B anomalies. And for each of B to S mu mu and B to C tau nu, there was work trying to explain them with new physics, and it was found that new physics that couples purely left-handedly was preferred. Given this, we were able to show that it's possible to have simultaneous explanations of these two decays. The main thing is to notice that, okay, this is a bit more technical, that the left-handed C quark and the left-handed S quark are basically in a doublet, so that it's possible to relate these two different decays. So we proposed a model that could do this. We proposed a model, a vector boson model, in which we added a Z prime to explain B to S mu mu and a W prime to explain B to C tau nu, and they're part of a triplet. And there are other models which involve leptoquarks. Subsequently, with a bunch of different collaborators, we compared all these models And we found that the only viable explanations were this original vector boson model and a particular leptoquark model called the U1. Very recently, in December, LHCb announced that some of the beta S L plus L minus anomalies had gone away. They had mismeasured things with involving electrons. So we'll have to look at this once again. So where do we stand today? As I've told you, there are already a number of observations that the standard model can't explain. Neutrino masses, dark matter, baryonic symmetry of the universe. In addition to that, there are now a number of measurements that disagree with the predictions of the standard model. Okay, the B anomalies I already described, but the measurement of the mass of the W, the ratio mz over mw disagrees with the standard model prediction by a huge amount. The anomalous magnetic moment of the muon, also the measurement of it also disagrees with the standard model prediction. And there are a variety of other things. VCB measured in two different ways. The values disagree. There's the Cabibbo anomaly, the beta pi k puzzle. Basically, there's a whole bunch of measurements now in which there are disagreements with the standard model. And then very recently, my collaborators and I found a new anomaly which we call the U-spin puzzle. Okay, so this brings me to my final thing. Basically, my entire career has been devoted to the search for this new physics, and I've described a bunch of things that I've done. Right now, there are a lot of hints of new physics, and so, as I say, it may be wishful thinking, but it seems to me that we're close to finally finding this new physics. Okay, thanks. I'll stop here.
Okay, thank you very much, David. Everybody can show their appreciation by either putting up a thumb or some indication that you have appreciated his reaction. So I am looking for I can't do it. Anyway, thank you very much, David. Excellent talk. We should now move to questions and answers. Are there any questions? Have you put questions in the chat that I could read, or you can directly unmute yourself and ask the questions? So exactly for this reason, I have a couple of questions, David.
Okay, so, I mean, Rich asked the question.
Rich asked the question.
What's the most plausible explanation for MW over MZ not being? I don't have a specific answer, but it suggests that there's new physics in the Higgs sector. I don't know specifically what kind of new physics can account for it. I haven't read all the papers, but there have been a variety of suggestions, and they all seem to point at a new Higgs structure.
Okay. And just a question, what experiments do you think are the most important for seeing the new physics?
Okay, that's a good question. It's a bit complicated. Ideally, of course, we would like to produce just build accelerators with higher and higher energies and produce new particles. That's the most obvious way of seeing new physics. But LHC has done that and hasn't found anything. So now we have to go the indirect route and look at very rare processes and see if their measurements disagree with the standard model. Those are the so-called indirect measurements, and those are good. We start to see some very important signals. This said, even if we establish that there's a statistically significant discrepancy, no one will be satisfied until we actually find the new particles. And so we're going back to having to produce them directly. It's the same with dark matter. Everyone believes that dark matter exists, but until we've actually detected it, through various experiments, nobody will be really satisfied.
Okay. And that was actually my second question. Do you think this new physics that is obviously tantalizing us has to do with dark matter?
Okay, you're asking a non-physics question. Do I believe? Do I believe? Yeah. One would think, okay, clearly in the theory of everything, it's all connected. But at this stage, it could be just two different things. I've done work trying to connect the B anomalies and dark matter, and other people have, we play this game all the time. And there are explanations in which they're connected, but there are other explanations in which they're not connected. So I don't have a definitive answer to that.
It's fine. I think that covers my questions. Are there any other questions in the audience? I don't see anything in the chat, so I think we'll move on to the next stage, where I'm going to read the citation. So David, you have won the CAP-CRM Prize in Theoretical and Mathematical Physics in recognition of your outstanding contributions to the theory of elementary particles, including trailblazing contributions to the analyses of B meson decays and CP violation in the standard model of particle physics. So congratulations, and I wish I could be there to shake your hand and pat you on the back.
Okay, so thank you very much.
Can you give a short speech? Yeah.
Right. So thank you very much, Manu, and thank you to the CAP and the CRM for this award. It's much appreciated. I have to say that as you saw, okay, I've worked on lots of different things, and I've collaborated with lots of different people. I rarely write single authored papers. I much prefer to collaborate. And so I have to give a big acknowledgement to my collaborators, my postdocs, my students over the years. Okay, there's another question that has appeared. Okay. Okay, so I have to I acknowledge my collaborators over the years. Let me just say that in the very early years, when I was a student or a postdoc, I did some of these calculations. I went off and I just played with things, showed them to my advisor, and they said, "Oh, this is a good result." I didn't know it was a good result. So they said, "This is a good result, we'll write it up." 20 years later, 25 years later, now my students and postdocs do the same thing. They go off and they do things, and I look and say, "Oh, that's a good result." So what goes around comes around. Thank you very much for the award.
Most welcome, and of course you are invited to come to the CAP Congress, where we will give you the medal in person at the banquet. Okay. Okay. Do you want to answer Sriram's question?
Sure. This was
the discovery of the Higgs boson helped in finding new particles.
Nope.
No. Okay.
Nope. When the Higgs boson was discovered, I had people who said, "Oh, you found the Higgs boson. This must change everything." And I had to say, no, we knew it was there. I mean, we didn't know what its mass was. It had to be there just because it was part of the standard model. So its discovery just confirms that the standard model is correct, but it doesn't tell us how to go beyond.
Okay, so thank you very much, David.
Okay, and I fell well within your 40-minute range.
I need advice from our executive director. Do we wait 5 minutes or do we go to the next one?
We'd like to thank everybody for attending the talk by David, and congratulations, David, on your achievement. We will be starting the next talk at 10:40, as was posted and announced to everybody. So there is a bit of a short break right now, but we would really welcome and invite everybody to stay on and listen to the talk by Dr. Arvanitaki.